Welcome to our exploration of the power rule, one of the most fundamental and useful tools in calculus. The power rule is essential for finding derivatives, which tell us how functions change. The power rule applies to functions in the form f of x equals x to the power of n, where n can be any real number. This simple pattern appears everywhere in mathematics and science. In simpler terms, the power rule tells us how these functions change as x changes. This is called finding the derivative, and it gives us the rate of change at any point. The power rule is widely applied across many fields. In physics, it helps us understand motion and forces. Engineers use it for optimization and design. Economists apply it to model growth and change. Data scientists rely on it for machine learning algorithms. In this comprehensive tutorial, you'll learn how to identify when to use the power rule, master the step-by-step application process, work with different types of exponents, including fractions and negatives, and solve real-world problems. By the end, you'll have the confidence to apply this powerful tool in any situation. Remember, it all starts with recognizing functions in the form x to the power of n. Keep this formula in mind as we dive deeper into the mechanics of the power rule. The first and most crucial step in applying the power rule is learning how to identify the exponent in any function. This skill forms the foundation for everything that follows, so we need to master it completely. Every function we'll work with has the general form f of x equals x to the power n. Our job is to identify this exponent n, which can be a positive number, a negative number, or even a fraction. Let's start with our first example. We have f of x equals x to the fifth power. Looking at this function, we can clearly see that the exponent is 5, so n equals 5. This is a positive integer exponent, which is the most straightforward type to identify. Now let's look at a fractional exponent. Here we have f of x equals x to the 1/2 power, which is the same as the square root of x. The exponent n is the fraction 1/2. Fractional exponents represent roots, and it's important to recognize them in both forms. Here's an example with a negative exponent. We have f of x equals x to the negative 2 power, which can also be written as 1 over x squared. The exponent n is negative 2. Negative exponents indicate that we're dealing with reciprocals or fractions. Here's a tricky example that students often miss. We have f of x equals 1 over x cubed. At first glance, it might not look it has an exponent, but remember that any fraction with x in the denominator can be rewritten using negative exponents. We can rewrite this as f of x equals x to the negative 3 power. Now we can clearly see that the exponent n equals negative 3. This is why it's important to recognize different forms of the same function. Let's summarize the key points for identifying exponents. Always look for the exponent on x. Remember that n can be positive, negative, or fractional. Square roots and other roots are fractional exponents, and fractions with x in the denominator become negative exponents. Mastering this identification step is essential for applying the power rule correctly. Now that we've identified the exponent n in our function, we can apply the power rule. The power rule formula states that the derivative of x to the n is n times x to the n minus 1. Applying the power rule involves exactly two operations that we perform in sequence. First, we multiply the original function by the exponent n. Second, we subtract 1 from the original exponent. Let's see this in action with a concrete example. We'll start with the function f of x equals x to the 4th power. Here we have f of x equals x to the 4th power. We can see that our exponent n equals 4. Step 1, we multiply by the exponent. Since n equals 4, we multiply x to the 4th by 4, giving us 4 times x to the 4th. Step 2, we subtract 1 from the original exponent. 4 minus 1 equals 3, so we get 4 times x to the 3rd power. This is our final derivative. Let's try another example to reinforce this process. This time we'll differentiate f of x equals x to the 7th power. Here our function is f of x equals x to the 7th power. Our exponent n equals 7. Applying both steps, we multiply by 7 and subtract 1 from the exponent. 7 minus 1 equals 6, giving us 7 times x to the 6th power. One more example to make sure we have this process down. Let's differentiate f of x equals x to the 2nd power, which is simply x squared. Starting with f of x equals x squared, where n equals 2. First, we multiply by the exponent 2. Then we subtract 1 from the exponent. 2 minus 1 equals 1. This gives us 2 times x to the first power, which simplifies to just 2x. Notice how x to the first power is simply x. Remember, applying the power rule always involves these same two operations. Multiply by the exponent, then subtract 1 from that exponent. This mechanical process works for any power of x. Now that we've applied the power rule to find our derivative, we reach the crucial third step, simplifying the result. This step transforms our raw derivative into its clearest, most useful form. There are several common types of simplification we encounter when working with derivatives. Each type serves to make our final answer more readable and easier to work with in subsequent calculations. Let's start with our first example. After applying the power rule, we have f prime of x equals negative 2x to the negative 3 power. Notice the negative exponent here. Remember our rule for negative exponents. X to the negative n equals 1 over x to the positive n. We'll apply this rule to simplify our expression. First, we convert x to the negative 3 into 1 over x cubed. This gives us f prime of x equals negative 2 times 1 over x cubed. Finally, we multiply the constants to get our simplified result. F prime of x equals negative 2 over x cubed. This is much cleaner and easier to work with. Our second example involves a fractional exponent. After applying the power rule, we have f prime of x equals 3/4 times x to the negative 1/4 power. Step 1, we convert the negative fractional exponent. X to the negative 1/4 becomes 1 over x to the positive 1/4. Step 2, we multiply the fractions. 3/4 times 1 over x to the 1/4 gives us 3 over 4x to the 1/4. This is our simplified form. Our third example is more complex, involving multiple terms with different types of exponents. We have 6x squared plus 2/3 x to the negative 1/3 minus 4x to the negative 2. We need to simplify the terms with negative exponents. The first term, 6x squared, is already in its simplest form, so we focus on the second and third terms. For the second term, 2/3 x to the negative 1/3 becomes 2 over 3x to the 1/3. For the third term, 4x to the negative 2 becomes 4 over x squared. Putting it all together, our final simplified derivative is 6x squared plus 2 over 3x to the 1/3 minus 4 over x squared. Each term is now in its clearest form. Remember these key points about simplification. Negative exponents become fractions, fractional exponents follow the same rules, multiply constants carefully, and always aim for the clearest possible form. Proper simplification makes your derivatives much easier to work with in future calculations. Now we'll explore how the power rule works with fractional exponents. Fractional exponents represent roots, and the power rule applies to them just as it does to integer exponents. Let's start with our first example. We want to find the derivative of f of x equals x to the 1/2 power, which is the same as the square root of x. To find the derivative, we apply the power rule. We multiply by the exponent 1/2, then subtract 1 from the exponent. Now we simplify the exponent. 1/2 minus 1 equals 1/2 minus 2/2, which equals negative 1/2. Finally, we can rewrite this using radical notation. X to the negative 1/2 equals 1 over x to the 1/2, which is 1 over the square root of x. For our second example, let's work with a more complex fractional exponent. We want to find the derivative of f of x equals x to the 2/3 power. Applying the power rule, we multiply by the exponent 2/3, then subtract 1 from the exponent. To subtract 1 from 2/3, we need a common denominator. 2/3 minus 3/3 equals negative 1/3. We can rewrite this as 2/3 divided by x to the 1/3 power, which is the same as 2/3 divided by the cube root of x. For our final and most challenging example, we have a function with multiple terms, each having fractional exponents. We need to find the derivative of f of x equals 3x to the 3/4 power plus 2x to the 1/3 power. We differentiate each term separately. For the first term, we multiply the coefficient 3 by the exponent 3/4, then subtract 1 from the exponent. 3 times 3/4 equals 9/4, and 3/4 minus 1 equals 3/4 minus 4/4, which equals negative 1/4. Now for the second term, we multiply the coefficient 2 by the exponent 1/3, then subtract 1 from the exponent. 2 times 1/3 equals 2/3, and 1/3 minus 1 equals 1/3 minus 3/3, which equals negative 2/3. Combining both terms, our final answer is 9/4 x to the negative 1/4 power plus 2/3 x to the negative 2/3 power. We can also write this using radical notation as 9/4 times the 4th root of x plus 2/3 times the cube root of x squared. Remember, the key to working with fractional exponents is to treat them just like any other exponent when applying the power rule. Multiply by the exponent, subtract 1, and then simplify your result. Now we'll explore how the power rule works with negative exponents. Negative exponents represent reciprocal powers, and understanding them is crucial for differentiating rational functions. First, let's recall what negative exponents mean. A negative exponent indicates that we take the reciprocal of the base raised to the positive version of that exponent. For example, x to the negative 1 equals 1 over x. X to the negative 2 equals 1 over x squared, and x to the negative 3 equals 1 over x cubed. Now let's see how the power rule applies to these negative exponents. Remember, the power rule states that the derivative of x to the n equals n times x to the n minus 1. Let's start with our first example. Find the derivative of f of x equals x to the negative 1. Step 1. Identify the exponent n. In this case, n equals negative 1. Step 2. Apply the power rule. We multiply by the exponent and subtract 1 from the exponent. Step 3. Simplify the exponent. Negative 1 minus 1 equals negative 2. We can also write this as negative 1 over x squared, which is often the preferred form for negative exponents. Now let's try a more complex example. Find the derivative of f of x equals x to the negative 3. Step 1. Identify n. Here n equals negative 3. Step 2. Apply the power rule. We get negative 3 times x to the power of negative 3 minus 1. Step 3. Simplify the exponent. Negative 3 minus 1 equals negative 4. The final answer is negative 3 over x to the 4th power. For our final example, let's include a coefficient. Find the derivative of f of x equals 5 times x to the negative 2. Step 1. Identify the coefficient and exponent. The coefficient is 5 and n equals negative 2. Step 2. Apply the power rule. The coefficient stays, and we multiply by the exponent and subtract 1 from it. Step 3. Simplify. 5 times negative 2 equals negative 10, and negative 2 minus 1 equals negative 3. The final answer is negative 10 over x cubed. Remember, when working with negative exponents, the power rule works exactly the same way. The key is to be careful with your arithmetic when subtracting 1 from a negative exponent, and to express your final answer in the clearest form possible. Now that we've mastered the power rule mechanics, it's time to see how this fundamental tool applies to real-world problems across multiple disciplines. The power rule isn't just theoretical, it's essential in physics, economics, and modern data science. Our first application comes from physics, where the power rule helps us find velocity from position functions. This is fundamental to understanding motion in the physical world. Consider a falling object whose position is given by s of t equals 16t squared, where s is measured in feet and t in seconds. To find the velocity at any time, we need to differentiate the position function. To find velocity, we differentiate position with respect to time. Using the power rule on 16t squared, we multiply by the exponent 2, then subtract 1 from the exponent. Simplifying this expression, 16 times 2 equals 32, and t to the power of 2 minus 1 equals t to the first power, which is simply t. This tells us that velocity equals 32t feet per second. At t equals 2 seconds, the velocity would be 64 feet per second. The power rule made this calculation straightforward and immediate. Moving to economics, the power rule is crucial for finding marginal revenue, the additional revenue generated from selling one more unit of a product. Suppose a company's revenue function is r of x equals 100x minus x squared, where x represents the number of units sold. To find marginal revenue, we differentiate this function. Marginal revenue is the derivative of the revenue function. We apply the power rule to each term separately. For 100x, we get 100. For negative x squared, we get negative 2x. Simplifying 100 times 1 times x to the 0 equals 100, since x to the 0 equals 1. And 2 times x to the first equals 2x. This marginal revenue function tells us that when 20 units are sold, The marginal revenue is 100 minus 40, which equals $60 per additional unit. This information is vital for pricing and production decisions. In modern data science, the power rule is fundamental to gradient descent algorithms, which are the backbone of machine learning and artificial intelligence. Consider a simple cost function j of theta equals theta squared, where theta represents a model parameter we want to optimize. To minimize this cost, we need its derivative. The gradient descent algorithm requires the derivative of the cost function. Using the power rule on theta squared, multiply by the exponent 2, then subtract 1 from the exponent. This gradient, 2 theta, tells the algorithm which direction to move the parameter. If theta equals 3, the gradient is 6, indicating the algorithm should decrease theta to minimize the cost function. These three examples demonstrate the power rule's versatility across disciplines. Whether calculating motion in physics, optimizing business decisions in economics, or training AI models in data science, the power rule provides the mathematical foundation. By mastering the power rule, you've gained a fundamental tool that opens doors to advanced calculus topics like integration, optimization, and differential equations. This single rule connects abstract mathematics to practical problem solving. Remember the simple pattern. Multiply by the exponent, then subtract 1 from the exponent. This pattern, applied consistently, solves problems from calculating the speed of falling objects to training the next generation of artificial intelligence. Thank you for joining me on this journey through the power rule. If you found this helpful, please like this video and subscribe for more calculus tutorials. Leave a comment about which mathematical topic you'd like to see next. Keep practicing, and remember, every expert was once a beginner who never gave up.